So we're ready to look at the x squared function. If we want to find the graph of y equals x squared, and I have set up my table already for you. I've got these x's that I'm going to be putting into my function. You might be asking, how do I know what needs to go in for x? Well, most of these, if there's anything, any kind of, you might say action, if there's anything happening that changes the graph, most of the time it generally will be happening right around the origin here. So most of the time I try to put in a couple of values that are smaller than 0, a couple of values that are bigger than 0, just so that I can see what's happening to the graph whenever it makes any kind of changes. So I'm going to let you pause the video. You should be able to do this yourself. I want you to substitute each of these numbers into your function and fill in your y column. And then either plot the points by hand or look at it on your calculator and go ahead and fill in this graph. And then we'll talk about the domain and the range. Okay, so you should have gotten for your y values positive 4, positive 1, 0, 1, positive 4. So we're going to take each of these ordered pairs and locate them on our graph. Negative 2 on x and positive 4 on y is going to put me about right here. Negative 1 on x, positive 1 on y puts me here. And then I've got a point at the origin. I've got ordered pair 1, 1 and ordered pair 2, 4. Now look carefully at your graph before you go to connect your dots. This is not going to create straight lines. We talked a little bit before about how the exponent gives us some information about our graph. If we had y equals x to the first power, we would expect to see straight lines somewhere, or at least straight segments. With this having an x squared, I'm expecting it to look like some type of curve. As a matter of fact, it's a quadratic, so it's actually going to be a parabola. Alright, so with that information, when I go to connect the dots, I need to take into account what type of graph am I expecting to see. And this is going to be a curved shape. And we get this parabola that's centered at the origin and it opens up. Okay? What about the domain? Well, the domain would be, you can think of this looking at it as an equation or looking at it as a graph. The domain would be the possible x values that would give you a legitimate value back. So just looking at it here, you could probably see that you can put anything in here that you want for x, and it's still going to give you a y value. Looking at it graphically, we're looking along the x-axis. As we move from the left side of the graph to the right side of the graph, what x values will be included in this graph? Well, if you look at the ends, we've got these arrows, and they indicate that it goes forever, and it goes up forever, and it gradually will spread out in both directions forever. So as I'm moving in from the left side, my beginning point on my graph would be at negative infinity, and it's going to continue all the way out to positive infinity. So my domain, I could say it's all real numbers, or I could say it's negative infinity, comma positive infinity. For my range, I'm looking at all possible y values. So again, you can look at it this way with the graph. Just think about what happens if you start putting in numbers for x and squaring them. What kind of answers are you going to be getting back? Well, if you square it, you're only going to get positive answers back. Looking at it graphically, you're interested in what's occurring along the y-axis. So you're going to start at the very bottom at the smallest possible value for y you can start with and move up, and you're looking for when the graph actually begins. The graph actually of this x squared function begins right here at the origin. So that's going to be the smallest y value. And then it's going to go up to positive infinity. So we can say that our range is going to be square bracket, 0, comma, positive infinity. Example 2, we're looking at the square root function. So we've got y equals square root x. Again, we generally expect any changes in the graph to occur around the origin, so we're still starting out with these same x values. If something doesn't work, then we'll just throw it out and we'll look for something else that might. So go ahead and pause the video, substitute these x's in, see what you get back. If you have some that don't work, then think about what else might work. So take a moment to do that and see if you can come up with an idea for what you think the graph might look like. Okay, so the first thing you might have noticed is that when you put in a negative x, when you put in negative 2, you're trying to find the square root of negative 2. All right? We are not going to try to graph complex numbers. We're going to stick with the real numbers here. So in this case, when you put in your negative 2 and try to take the square root, you're not going to get a legitimate value back that you can work with. So the negative 2, we're just going to eliminate the negative 2. Same thing with the negative 1. If we try to take the square root of negative 1, we're getting a complex number, and we're not going to graph a complex number. So we can eliminate those two possible x's. They're not giving us y values back that we can graph. If we put 0 in for x, you should have gotten 0. Square root of 0 is 0. If you put in 1 for x, you should have 1. If you put in 2, you're going to get a decimal, and that's fine. It will be approximately 1.4. Okay, but to make it a little bit easier to graph, maybe we should put in a number that's a little bit easier to work with. What's a nice number that I can put in for x? Well, a perfect square would be 4. So let's put in 4 for x, and then that's going to give me a 2 back. I like that a little bit better. So I've got ordered pair 0, 0, 1, 1. I could graph 2, approximately 1.4, and then I can also use order pair 4, 2. So 0, 0, 1, 1, 4, 2. Again, before you connect your dots, think about what you've got here. Now, I haven't really told you anything about what to expect. If you've got, this would be x to the 1/2 power. Okay, so that's going to be, I haven't told you anything about what to expect there. But it is going to be a curve. You're going to start at the origin, and then you're going to draw a curved shape through these dots, and it will go out to positive infinity like this. So this is what your graph should look like. Really, it looks like if you were to take that parabola that you got from the x squared function, lie it on its side, and then chop it in half and only take the top half of it, then you would have a graph that looks like the square root function. What about the domain? What do you think the domain is going to be? Well, as we move in from the left side of this, looking at the x values, the graph does not even begin until we get to the origin. So x equals 0 is going to be my starting point, and it goes out to positive infinity. So my domain, I would use a square bracket, 0, comma, infinity. For my range, y values, I'm going to go to the bottom and go up. My graph begins at the origin, so from y equals 0, and it goes up forever to positive infinity. So my range in interval notation would be square bracket, 0, comma, infinity. This time we want to graph the function y equals x cubed. Again, you can substitute these values in for x, fill in your y column. Maybe they'll work, maybe they won't. I'll let you decide. And then see if you can come up with what you think, at least plot your points. Maybe wait for me before you connect your dots so we can talk about what kind of an image we should be seeing in our graph. But go ahead and take a moment and fill in your table and try to graph your points that you plotted on the try to plot your ordered pairs that you get from your table. So in your table, your y values, you should have -8, -1, 0, 1, +8. Now let's plot those points. Okay, so your points should look very similar to mine. And it should be something where you should be able to kind of connect it with this like swoosh movement here. So really what you have with the x cubed function, one side of it, on the right side of the y-axis, looks like half of a parabola that opens up. And then on the left side of it, it looks like half of a parabola that opens down. Okay, so this is your x cubed function. It gradually spreads out just like the x squared function did. So for our domain would be negative infinity to positive infinity. Our range goes from negative infinity to positive infinity on the y's. Okay. Function 4 is the cube root function. Y equals the cube root of x. Again, I would like you to fill in your table and plot the ordered pairs that you find, and then we'll talk about how to draw your graph. So go ahead, pause the video, do your table, and plot your points. Okay, so this time, when you put in -2, you should have gotten a decimal. If you don't want to graph the decimal, that's fine. Let's think about a number that we could put in for x that would give us a whole number back that we didn't have to round. If you're doing a cube root, what's a good number to put in here for your x? What if we put in a -8? Because 8's a perfect cube. And then let's put in a +8 down here. Again, you don't have to put in these numbers. If you put in the numbers that I had originally and use the decimals, that's fine too. If I put in -8 for x, I'm going to get -2. And then I'm going to have -1, 0, 1, +2. So let's plot those points. Alright, so you should have something similar to mine. If you did the -2 for x and graphed the decimal, you probably did not get a very good enough of a picture to know how to graph it, because in the middle they're just lining up. And if you put in -2 and got a decimal, then you will probably right around here somewhere. So the -8 and the +8 for x give us a little bit better idea of how to draw our graph. Alright, what does this look like? Does it look similar to something you've already seen? If you go back and look at the graph that you just did for the x cubed function, it was this S sort of shape. And this time we have the same thing happening, but instead of it being this way, now it looks like it's kind of wrapping around the x-axis. So you've got what looks like half of a parabola on its side, and then the other half under the x-axis on this. So that's what your cube root function should look like. What is our domain? We're going from negative infinity to positive infinity along the x-axis. What about our range? What do you think it should be? Starting at the bottom of the graph begins here, but it's got an arrow, so that means that as it goes out, it also gradually spreads up and down. So it's going to start at negative infinity on the y-axis, and it's going to go up to positive infinity on the y-axis. So our range and our domain and our range are both all real numbers for the cube root function. So again, you need to kind of commit this to memory. Cube root function is this kind of S-looking shape that's long and flat around the x-axis. So before we talk about function 5, the semicircles, just want to kind of remind you that from high school we have this equation of a circle, which we know is a circle centered at the origin has the equation x squared plus y squared equals r squared, where r is your radius. We're not really that interested in graphs of circles, though. I don't know. I'll let you think about why for a moment. I don't really want to tell you yet. But if you think about what we're working with in this chapter in general, and think about a circle, why would it not be as pertinent to us as some of the other things we've been talking about? All right, we'll talk about that in a moment. But knowing that the equation of a circle is x squared plus y squared equal r squared, if we were to solve this for y, we would get the equation of a semicircle. The equation of a semicircle would be this y equals plus or minus the square root of r squared minus x squared. Okay? So with this knowledge, we can now talk about how we can graph semicircles. We're not really going to be doing a lot of plotting points for the semicircles. You can if you want to. But if we know that this is centered at the origin and we know how to find our radius, that's really all we need, all that we need in order to graph this. So let's move on to number 5. All right, we are asked to graph the equation y equals negative square root of 4 minus x squared. Again, feel free to use a graphing calculator to help you out with this as well. All right, just looking at this, I know that it's centered at the origin, and I know that my radius would be the square root of my constant, so the square root of 4, so r is 2. So I just need to go to the center, go to the origin here, and I want to use my radius of 2. So I can go out here and here, 2 spaces. All right, and then also notice that there's a negative in front of this one. If there's a negative in front of it, then you're going to be looking at the bottom underneath the x-axis. So really, whatever y values are coming out of that radical, out of that square root, you're going to negate them and put them down here. So we can, if we have a radius of 2, that means we can come down 2 spaces, and then we can connect these dots with a semicircle. Now that you've got the picture to look at your semicircle, do you have an idea as to why I'm more interested in a semicircle than I am in a circle? Think about it for a moment if you haven't already. But essentially, we're working with functions here. This one, is this a function? And how do I know? Does this pass the vertical line test? Yeah, it does. So this is a function. A circle, on the other hand, is not a function because it doesn't pass the vertical line test. So that's why we're more interested in a semicircle than we are in a circle. All right? So as far as how to graph a semicircle, you just need to understand how you can find your radius. It's going to be the square root of your constant. And then you have to look at the sign in the front. If you don't see a sign in the front, then it's going to be above the x-axis. If you've got a negative in front of it, then it's going to be below the x-axis. What is a domain? All right, this is a little different from the ones that we did earlier. The other ones that we were doing tended to go out to infinity in one direction or the other. This one has a beginning and an end. If we do the domain from left to right, the graph begins when x equals negative 2, and it ends over here when y equals positive 2. So my domain, I can use a square bracket, negative 2 comma positive 2 square bracket. And for my range, so go from the bottom up, it begins here. This will be negative 2 on the y-axis, and it goes up to the origin. So square bracket, negative 2 comma 0. Another very important function that you need to be able to pretty much know inside and out is the absolute value function. So we're going to want to graph y equals absolute value of x. I'll let you work on this yourself, so go ahead and pause the video. Decide if these numbers are going to work. A lot of times they do work, but every once in a while, as we've seen, they're not the best choices. But I'm going to let you decide about that and go ahead and plot your points to try to get an idea of what you think the graph needs to look like. So you should have gotten 2, 1, 0, 1, 2 for your y values. All right, just the dots alone are going to look like this. Then we have to think about how to connect these dots. Would it make sense to connect these using like line segments or array or curve of some sort? What kind of exponent do I have on my x? This is the x to the first power. All right, and if you look at the numbers that you were getting, you had 0, 0, 1, 1, 2, 2. They're lining up perfectly. You could continue. You would have 3, 3, 4, 4, etc. So these are going to line up in a linear fashion for us. And this is going to create a V-shaped graph. Okay, so I tell people to help them remember, when you're trying to remember which equations have which graphs have which shapes, if you think about the V, absolute value has a V shape, hopefully that will help you to remember that's what it's supposed to look like. And of course you can still graph it on the calculator, but you really need to be able to know right away. Absolute value is a V shape. So this is what my graph looks like. What is my domain? Negative infinity all the way to positive infinity. We're back to these arrows, and they go forever in both directions. What do you think my range needs to be? Starting down here, the graph does not come below the x-axis. It only begins here when y equals 0, and then it goes up to positive infinity. So the range would be square bracket 0, comma, infinity. The next thing we're going to talk about are piecewise functions. As the name suggests, a piecewise function is graphed in pieces, essentially. It's going to be defined differently depending on where you are in the domain. For example, maybe if x is less than 4, meaning that I'm going to be like from here back, my function might be doing something up here. But maybe when x is greater than 4, so on this side of the graph, it might be doing something completely different and somewhere down this way. And it can also be, it could look like a parabola in one portion of the graph, and then it might switch over to like a straight line in another section of the graph. So we essentially are just taking increments of different graphs and putting them together to create a piecewise function. We've got two examples that we need to do. So we want to graph f of x equals, this is going to be 1 if x is less than 2, and then it's going to be defined to be negative 1 for x values greater than or equal to 2. So I'm going to look at my t-table, and I'm going to start putting numbers in for x. Students always ask, how do I know what to put in for x? Well, I tried to look at this piece of my definition for this problem. I know that the function is doing one thing on one side of 2, and it's doing something else on the other side of 2. So when I do my t-table, I need to put in a few values on each side of the number 2. So, and again, it's because this is where the change is occurring around x equal 2. So I need to put in, I'm going to put in negative 1, 0, and 2. Let me do that again, I'm sorry. Let's put in 0, positive 1, and 2. And then put in a couple of numbers that are bigger than 2, so 3 and 4. But general rule of thumb here is I need that kind of middle number in this list to be where this change occurs, where they change around x equal 2. All right? So this tells me that starting with x equal to 0, if x equals 0, I have to decide if I'm going to be looking in the top piece or the bottom piece of my function. Well, x equals 0, if I put it here, 0 is less than 2. That's true. So that means I'm going to use this definition. I'm going to use 1. So if x is less than 2, y, my function value will be 1. So I put a 1 right here. If x equals 1, again, I have to decide, do I go to the top or to the bottom? If I've got 1 is still less than 2. So that puts me here. So this is my function value. So 1 there as well. If x equals 2, this time I'm looking at the bottom. If x equals 2, I'm going to use this definition. So my function value is -1, or my y value will be -1. If x equals 3, 3 is greater than 2, so I'm going to use this part. I'm going to use -1 for my y value. If x equals 4, still going to be here. 4 is greater than 2, so my function value, or my y, will be -1. So now we can plot those points. X equals 0, y equal 1 would be here. Order pair 1, 1 is going to be here. Order pair 2, -1, so over 2 and down 1. Order pair 3, -1 is here. And 4, -1 puts me here. So I've got 2 flat lines, basically. All right, on the left, so we've got the dots in here. How are we going to fill this out? Again, the graphing calculator can help you with this, so that you can use that as an aid. But doing this by hand, how do I fill in these pieces? If you want to see what's going on back here, go ahead and put in some negative values for x. If you put in -1, what would you get for y? Well, if you put in -1 for x, that puts you in this piece because -1 is less than 2, so you would get +1 for y. So that would give you this. If you came back here and said, I don't know, if x equals -4, that still puts you in the top, so you're going to get +1. So if you put more in, you can see that all this is going to go back to -infinity, just as a flat line. Over here we've got dots starting when x equals 2 and extending out to +infinity. All right, but we've got a little bit of a gap here. My function is defined up to x equal 1, then I've got a space, and then x equal 2 is doing something else. So I've got to make sure that I have everything in here included in my graph. So what if I'm between x equal 1 and x equal 2? What happens? So let's say if I put in 1.5. If x equals 1.5, 1.5 is still less than 2, so y would be 1. So if you want to write that on here, if I put in 1.5 for x, my y is going to be 1. So 1.5 on x, 1 on y gets me there. And you can put in other numbers that are closer and closer to 2, like if you put in 1.8 or 1.9, it's going to get closer and closer up to x equal 2. However, if x equals 2, that's when it jumps down here. So we want to show that it's going to get all the way up to the 2, but it's not going to include the 2. And we can show that with an open circle at the 2 and extend the line like this. Okay? So that's what my graph would look like. It's going to be a flat line going through y equal 1 until I get to x equal 2. Then I've got the open circle, it jumps down, and then it's going to be at y equal -1, and it's going to stay there. Why do I need to put in that open circle? Well, with this being a function, it does still need to pass the vertical line test. And the open circle allows it to pass the vertical line test, because regardless of where I put my vertical line, remember my vertical line is only allowed to touch my graph one time. And with the open circle, it only touches the graph once when x equals 2. For 7b, we want to graph f of x equals x squared minus 4 for x between -2 and +2, or x minus 2 for x greater than 2. So this time, I think just like the last one too, is where the break occurs in the graph. Yeah. So again, when x equals 2, the graph is doing one thing over here, and it's going to be doing something different over here, or maybe it's down there. So when I go to fill in my x column in my table, I look at where the change occurred right here at the 2. And if you want to put in a -2, that's good too. That's fine. But I need to put in numbers on each side of +2 so that I can show whatever, so that I can make sure that I need to be able to see what's going on around x equal 2. So I'm going to put 2 in the middle, and then I can put maybe a 0 and a 1, and then over here a 3 and a 4. And I may have to put in more to get a good picture of what's going on with it. So when x equals 0, again, am I in the top or am I in the bottom? Well, 0 is between -2 and +2, so that means I need to be in the top. I put 0 here for x, I square it and subtract 4, so my y value is -4. When x equals 1, that's going to still put me up here because 1 is still less than 2. 1 squared minus 4 gives me -3 for my y value. When x equals 2, where am I now? All right, so if x equals, pay close attention to these inequalities. This says the top one x is less than or equal to 2, and then here x is greater than 2. So whatever number you're working with, it's only going to fit in one spot. So if x equals 2, I have to be up here still. So put 2 here for your x. 2 squared minus 4 would give me 0. When x equals 3, now I'm in the bottom because 3 is greater than 2. 3 minus 2 gives me 1. When x equals 4, 4 is greater than 2, so I'm in the bottom. 4 minus 2, my y value is 2. Okay, and now we can plot our points. We've got order pair 0, -4. Order pair 1, -3. 2, 0. 3, 1. 4, 2. Okay, now the dots are really not enough by themselves to tell us how to connect the dots or how to draw our graph. So you can always add more points. You can substitute more values in. I didn't come back here, and I would like to know what's going on the left side of the y-axis. So let's put in -1 and a -2 for our x. Let's see what we get. If I put in -1, where does that put me now? -1 is here. So I'm going to do -1 squared minus 4. So 1 minus 4 is -3. And if I put in -2, -2 is as far down as I get to go because that's the last number that's in the domain. If I put -2 here and square it, I get 4 minus 4, I get 0. All right, so -1, -3, find that ordered pair. It's here. And I want to find ordered pair -2 zeros here. Okay, so this is a good example of why it's important to know the shapes of the graphs that you're working with. Look at our original problem. We're asked to graph this x squared minus 4. That's the x squared, all right? And again, this is from -2 to +2. So between -2 and +2, in between these two numbers in this area, based on the function that I'm given, what should be happening with my graph? If I just look at this much of it, I've got these dots, like this, and that comes from the x squared function. So that is enough information to tell me how to draw it. With it being an x squared, it should be a parabola, so I can connect these dots using a parabola. And my graph is not perfect. It should be a little bit more like this, because my dots did not come out looking like a parabola. They look too straight. They look too much like a V. But it needs to be a parabola, because it's an x squared. So that's part of it. All right, so when x is greater than 2, what does it look like is happening over here? Well, now it looks like they're lining up in a straight line. Does it make sense? Let's go back and look at the function. When x is greater than 2, the function is defined to be x minus 2. Well, that's x to the first, which is just a straight line, so that obviously matches with what we've got here. So for any value of x greater than 2, so it means we're going to go out this way forever, we can go ahead and connect those dots and put an arrow indicating that it continues to infinity. Should there be anything back here? Why didn't I put an arrow on this piece? I've just got a dot. Well, that's because they told me that the function was defined beginning at -2 up to +2, and then it was defined for anything larger than +2 this way. So I need to just have a dot here, but not an arrow. But that's what my graph looks like. So you can see how this piece came from the x² function because it's a parabola, and this piece is just a linear function because it's a straight line. What if let's go ahead and practice with domain and range. What if we were asked to find the domain for this? What would it be? With your domain, you're going to go from the left to the right, looking for all possible x values. I'll give you a hint. You can also find the domain from looking at this up here. But just looking at the graph begins here when x equals -2. And then it continues all the way out to +infinity. All right, it includes that -2, so we'll put a square bracket, -2, comma, infinity. And then for your range, we're going to start at the bottom. The graph begins right here when y equals -4, and then it goes up to +infinity, because the arrow goes up forever. So square bracket, -4, comma, +infinity. So it's just a little practice for domain and range. We're asked to determine whether our function is increasing, decreasing, or constant. Okay, what is that? That essentially means that, and I'm sorry about the camera has changed and now you can only see my head. What that means is as x increases, what's happening with y? So on your graph, as you move from the left side to the right side, are your y values going up or are your y values going down? The easiest way to see this visually is that as you're going from the left to the right, and imagine if you're on this actual graph itself, as you go from left to right, are you going uphill or are you going downhill as you go along this graph? Okay, on this one you're going uphill, so this one is increasing. In part B, as your x values increase, as you go from the left to the right along the domain, what's happening with the y values? So if I come back here, as I move from the left to the right, going along this graph, I'm going downhill, so this one's decreasing. And then finally, part C. All right, here you've just got a constant function. It's flat. So as your x values increase, as you go from the left to the right on this graph, you are not going up or down, you're just staying in the same place. So this one is constant. So as the x values increase, the y values stay the same. So it's just a flat line, this one's a constant function. And that is it for section 2.2. So again, make sure that you understand that you have to, okay, I hope you can see that okay. Let me go adjust the board real quick so you can see it. Make sure that you remember that when you're working with section, those functions that we discussed, you are responsible for being able to recognize them just based on their equation. So you're going to need to remember that an x² function is a parabola. An x³ function is this like S shape. I call it an S shape. I don't know what else to call it, but it's a parabola that one side is flipped upside down, basically. And then you have to know what your square root function looks like, your cube root function looks like. You need to be able to recognize when you've got working with a semicircle. So the semicircle equations will be like a square root of a constant minus x². You just have to be able to recognize it when you see it. And absolute value function, you've definitely got to make sure that you know what the absolute value function looks like as a V shape. Okay, so work on these problems. We will be discussing these in class, and good luck with section 2.2.